Section 8.3, show that a quadrilateral is a parallelogram. Again, remember the parallelogram is defined as a quadrilateral with two or both sets of sides parallel. And we have our other theorems that show parallelograms. First of all, we have to decide what a converse statement is. Converse statement is a reverse statement. So if we said something like, if it's Sunday, then school is tomorrow. So if that's an original statement, the converse would say, if school is tomorrow, then it's Sunday. So this is the converse. Here's our original statement. So a converse just switches around a kind of a statement. Now why is this important? Because our theorems, 3 of the 4, are converses. So if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Okay, that is just the converse of theorem 8.3. Similarly, if we have a quadrilateral with both pairs of opposite angles congruent, the quadrilateral is also a parallelogram. Okay, and that is really the converse of theorem 8.4. Continuing with our last two here, if one pair of opposite sides of a quadrilateral are congruent and parallel, then it's a parallelogram. Now this is not a converse, this is a statement on its own. So for example, it looks like this. If I have parallel and congruent, and this is A, B, C, D quadrilateral, then A, B, C, D is a parallelogram. Okay. And finally, this one looks familiar. Again, it's a converse. This is simply the converse of theorem 8.6. So again, if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. So these are ways that we can show that a quadrilateral is a parallelogram. These 4 plus the definition make 5 ways. Continuing, we have typical type problems. Again, what theorem shows that these quadrilaterals are a parallelogram? Well, first of all, we have a quadrilateral here in A, and I know to find this angle I gotta take 360 minus 75 minus 105 minus 105, and that comes out to be 75. Now because of that, I can say that this is congruent to this, and then this is congruent to this. So by theorem 8.8, this is a parallelogram. Looking at B, well, this one's set up nicely here. I've got these are congruent opposite sides. These are congruent. So this is a parallelogram because of theorem 8-7. Letter C here, we got the parallels, and they're both 10, so they're congruent. So that's a typical theorem 8-9 parallelogram. And then finally D here, looks like I've got diagonals that are bisecting each other, 5, 5, 3.6, and 3.6. So this is theorem 8-10, which is the converse of theorem 8-5, or excuse me, 8-6. So typical type problems here. Now moving on, second type of problem you'll see here is what value for the variable will make the quadrilateral a parallelogram. Well, it looks like we've got these. That's in good shape. So possible diagonal is being bisected. And we want to say, hey, if I've got this, so that would mean that 2x minus 1 has to equal x plus 5. And that would be by theorem 8-10. Then I have myself a parallelogram. So again, let's subtract x. So x minus 1 equals 5. Add 1 to solve. So this is the value that will cause that to be a parallelogram. Now similarly, over here, again I'm looking at this being congruent to this. I'm hoping that this is the same as this. Okay, so in this case, if x plus 101 can be 180, and that would mean that both of these are 79. So when I subtract, I get 79. So that means 79 here, 79 here. Those are congruent. So this would in fact, by theorem, 8, 8, would give us a parallelogram. Now one final example here. First of all, on your notes, be sure I might have had quadrilateral here, so make sure to get that in place. And now let's plot. Be careful, scale factor here is 2. So -3 and then 4 gives me this from point A. -1, 2 gives me B. 7, 0 gives me C. And 5, 6 gives me D. So now I'm going to connect this up. And how to show that this is a parallelogram. Now we could use the distance formula to find all 4 sides and hope that we get opposite pairs are congruent. That will take some time, but probably a little bit quicker way is to go ahead and do a slope. Because slope is one way to find a parallel. So I'm going to find the slope here, which is up 1, 2, 3, 4, 5, 6, and over 1, 2. So it looks like the slope of AB is up 6, right 2, which gives me a slope of 3 over 1. Well, similarly, I'm going to find the slope over here, the opposite side. So 1, 2, 3, 4, 5, 6, 1, 2. And again, it looks like it's the same. So the slope of DC, I'll call it, again is up 6, right 2. So these are parallel. So now I can say that AB is parallel to DC. And we're in good shape there. So we're halfway there. Now let's go ahead and take a look at these two. So now BC, so the slope of BC is Looks like I'm going down 2 and then right. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. So down 2. 1, 2, 3, 4, 5, 6, 7, 8. Well, that took a lot. So down 2, right 8 gives me a negative 1/4. It does look like a negative slope because it's going down and to the right. The slope of AD looks like down 2, 1, 2, 3, 4, 5, 6, 7, 8. A little quicker that time. So down 2 plus 8, negative 4/1. So again, these are the same. So that means that BC is parallel AD. And because of the two sets of parallels, that's really not a theorem, that's our definition. So kind of jumping back here. So by definition, it's a parallelogram. And that concludes the formal notes for 8.3.